Problem 32. Here we have 2 kilogram. We have a mass M equals 2 kilogram is attached to a spring of K equals to 500 Newton per meter. The block is pulled 5 centimeter to the right. As you see here, is pulled to the right. So X equal here at this point. Let's say this position is position 1. At this position, we have X equals to 5 centimeter from the equilibrium and released from rest. At this point, we release the object. I mean, at this position, we don't have speed. Find the speed of the block as it passes through equilibrium. So we have to find the speed of the object. First of all, part A, if the horizontal surface is frictionless, we don't have interaction between the block and the object. So in part A, we have to find V at the position O. You know, the block will pass at this point. Let's say here we have V, and this one, the position O. Here we have VO. And we have a displacement between the between 1 to 2. Okay, here we have dx. Okay, now we have dx, we have f. We have to find the speed. Now, I think we cannot use Newton's law. We don't have enough information to use Newton's law. It's better to use, for example, you know, we can, because to find the velocity, you can find V in the kinetic energy. We can use the kinetic energy work theorem. You know, the total work equals to delta kinetic energy equal the kinetic final, not final, at the position O, the final point, because initially at the position 1 and finally at the position O. We take between, I take the relation between 1 to O. So the final point is O minus the initial kinetic at the position 1 between these 2 points. Okay, this is the relation we can write equals to half K X O square minus half, M over 2 V square at the point O minus half M V1 square at the point position 1. Okay, the total work. Now, in order to, initially at the position 1, V equals to 0. And I want to calculate VO. So the total work equals to M over 2 VO square. we have the value of M. I have to calculate the total work applied on the object. So we used this theorem to find VO. You have to think. If we talk about the velocity, you have to think about the kinetic energy work theorem. Okay? To find the total work, what we have on the object. Here we have mg down, we have n up, and we have fs to the left. Okay? And mg down. So we can write the total work applied equals to the work applied by fs plus mg plus n. We don't have mu, okay? We don't have friction, we don't have interaction. You know that n and mg are perpendicular to the displacement. Here we have the displacement, and here we have n, and here we have mg. Okay, the displacement to the left, n mg. The angle equals to 90. So the work done by n equals to the work done by mg equals to 0. So we don't have this one and this one. Finally, we get omega total equals to the work done by fs. You know, in the last videos, we calculated the work done by fs. It's equal to minus half k over 2 x final. I take between 1 to 0. So O is a final point, x0 square minus half k, the initial point is at the position 1, equals, so we can calculate omega total here. We substitute its value here to calculate VO, equals to minus, you know, at the position O, x equals to 0. So this one equals to 0. Minus times minus, we get plus. K equals to 500 divided by 2. X at this point, x1 equals to 5. 5 times 10 power minus 2. You have to put it in meter square. We get here omega total. Let's calculate its value. It's 0.625 joule. Okay, joule. This is the value of omega fs and omega t. We use now this relation. Okay, we can say VO square equals to 2 omega t divided by m. Okay, so VO equals to integral to omega total equals to 0.625 divided by m, which is equal to 2. We get 0.791 meter per second. This is the value. Here it's very important problem. I used the kinetic energy and work theorem to calculate VO. We don't have the total work applied on the block. We go to the calculation of the work omega Fs. We calculated this value before, and between these two relations we can find the velocity of the object at any point. You can choose any 2 points on the system. First of all, you have the initial position, and the final you have to precise between which points you are calculating the values. Here we have between 1 and 0. Maybe you can have between 1 and 2, any other positions. Here we have part B. We have to solve part B. We have to find the speed of the object at the position O if the coefficient, the kinetic coefficient, equals to 0.35. Here we use the same calculation, but we have a F, we have a resistance of F because the motion is to the left with Fs, and here we have the position 1, position 0, and we have to find VO. You know, we can use the same theorem, omega. Here we have omega, you know, in part A, we calculated omega Fs in part A. It was 0.79. No. It was 0.625 joule. Okay. Now, in this part, we use the same theorem, omega total prime equals to delta kinetic energy. I am using between position 1 and position 0. So, omega total prime, what we have here, we have, you know, for N and mg, we don't have any work, any effect of the work of omega N and omega mg. We have just the work done by Fs and by small f equals to final kinetic energy mvo square minus 0, because the object was at rest. Okay, we calculated already omega Fs, so I have to calculate the value of F. You know, here, be careful. F is opposite to the displacement, so it must be negative. And you put the value of F in absolute value. F times the displacement. Okay? And we have the value of omega Fs 0.625. It's in the positive direction. We put the sign times the magnitude in absolute value. The sign times the magnitude in absolute value. Okay? Okay. Equals to m divided by 2 VO square. Here, let's say we have 0.625 minus F equals to mu times N. Dx equals to, as I said, I have to put its value here, an absolute value. Here, absolute value. Okay? Dx equals to 0 minus 5, because at the final position we have 0 here, minus 5 times 10 minus 2. Don't forget an absolute value. Okay. This is the value of dx equals to m2 over 2 times VO square. Okay, here we have 0.625 minus mu equals to 0.35. N, to calculate N here, you have to apply Newton's law in function of y. You know, N is up, mg is down, we don't have motion equal to 0. So N equals mg equals 2 times 9.8. So here we can write 9 equals to 2 times 9.8 times the value here, absolute value, okay? Here we have 5 times 10 power minus 2 equals to VO square. We get, finally, VO equals to integral of the value here, we get VO as a position, let's say V prime, okay? Because it's a new V. We don't, it's not the same as before. We get here 0.531 meter per second. This is a new velocity as a position O, and as you see, it's less than the old one in the case where we don't have interaction between the block and the plane, because this in the case of interaction, this interaction, the friction, will resist the motion, so the velocity will be less. Okay, so we can say here VO in the case of mu, we have a mu, must be less than of VO in the case of mu equals to 0. Here we have 0.531, and before it was 0.791. Before, let me explain very important point. If you talk about Fs alone, okay, we have Fs. You know, in this case, Fs is in the negative direction, to the left, okay? You can say in direction of minus I. And the value will be kx. So kx is the magnitude of Fs, and minus I is the direction of Fs. Okay? If we take the block here, for example, here we have x. The same, you know, Fs must be directed toward x equals to 0. Here we have Fs. Fs equals also in the positive direction, plus I. And you put its magnitude kx. Okay? So the magnitude of Fs is kx. In this case, you have to put, look here, you have to put the value of the magnitude in absolute value. Okay? The value here in absolute value. So in the first case, in this case, x equals to 5. So minus k times 5I. The result we have minus 5ki. In this case, x equals to minus 5 if you want. But we have to put its value in the absolute value. In this case, we say plus k times minus 5 times I. Because the absolute value, we get 5ki. So this one is a magnitude. You have to put always the magnitude in the absolute value. And you put minus I and the plus I. It depends the direction of Fs. Okay? For this reason, when we applied Newton's law, what we said here, look here. We said Fs is to the left, or when we applied omega total equals to delta kinetic energy, we said omega total or omega Fs is to the left, we put minus to the left. After I put the magnitude of Fs equals to kx times the displacement, also absolute value. All the values here as absolute value, but here we have the sign plus or minus. In all the cases, we use plus and minus I, and you use the absolute value of kx. Okay? Thank you.